We got to hear a little bit from Eric yesterday, and I think you just scratched the surface on what you guys
Definitely
are planning to do. I know that imagery and change over time has been a really big interest, especially in almond orchards and all those things. So we're interested to hear a little bit more about what you have to fill us in on. So everyone, welcome Eric.
Thank you. Thanks everybody for joining. Today we're going to go a lot deeper in satellite imagery for ag tech. And again, to review from yesterday, our mission is to image the entire Earth every single day. And we do that with about 130 satellites going around the Earth today. How they work is they go north to south as the Earth turns, taking little strips of the Earth every time they come down. We have over 100 of the small satellites that look just like that one. We also have some bigger satellites, about 15 of them, that take high resolution images, and they're about the size of this podium. And to take a look at what that actually looks like, that's actually how they go down and take a strip of the Earth, picture after picture. The big satellites, we actually have to program to tell them where to point. And they take much, much higher resolution images of points on the Earth that are interesting to you. A couple interesting images. So this is Lancaster, California. And out in the desert, when it rains, when we get a really big wet winter, the flowers bloom. The flowers sometimes don't bloom for years, but when they do, enough of them bloom, we can actually see it from space. So all of that yellow you see there are flowers blooming. This is the Yarra Valley. If you've ever had any Australian wine, this is where it comes from. This is probably the most beautiful piece of agricultural land I've ever seen on a satellite. It's in New Zealand, nestled between a pair of mountain valleys with a big river going by. Here is St. Helena up north. If you go wine tasting after we're done here, that's a good spot to stop in. For anybody from the Midwest, we had a really wet winter in spring last year, and so here is Offutt Air Force Base, and here is Offutt Air Force Base after the flood happened. Pretty incredible how far that river moved.
Do you have Davenport, Iowa on there?
No, but we actually were giving images to the state of Iowa and the state of Nebraska to help them with their disaster planning. Here's a very recent picture from yesterday. You might have seen in the news yesterday that there was a rocket attack on a US base in Iraq. And this is actually that base in Iraq yesterday. And to zoom in a little bit, that's actually where the rocket impacted. We had these images 12 hours after the image was taken, after the attack. Luckily, no one was injured in that. Here's a time lapse of a few days in Brazil. Brazilian farmers, especially sugarcane farmers, tend to burn their fields. And so you can actually see the progression of the fire moving through the field from day to day. As I mentioned yesterday, we normally don't work directly with farmers. So very few farmers would come direct to Planet and buy our imagery and use it. We work through a lot of different partners who provide precision agricultural software, like FarmShots, Granular, Zarvio from BASF, Climate Corp from what is now Bayer, and Farmer's Edge. So if you're interested in what we're talking about today, that's where you'd get it. Today we're going to be focused a lot on precision farming, but there are other applications of this. Yesterday we talked a bit about pasture management in that use case in New Zealand. We're also seeing a lot of interest in ag lending and insurance. So for example, insurance providers can look at a farm and look at the productivity of that farm over time and look at the damage that's happened to it in previous years to assess how much the risk is on that site. Lending as well, they can look at the productivity of your farm when lending money. We're also seeing a lot of interest from traders, looking at our data to look at yields and look at storage of grain to predict the price of grain in the future. And we're seeing a lot of interest as well from consumer packaged good companies who want to verify sustainability. Sustainability is really hard to verify. So if you're a company like Anheuser-Busch or Coca-Cola and you want to certify that the farmer who's cut down the sugar cane that's going into my Coca-Cola has not burned down Amazon rainforest to expand their land, how do you do that? We could be one of the ways that you do that. What we're going to focus on today is precision agriculture and the areas in the crop cycle where satellite imagery can apply to precision ag. This can be in the planting stage with productivity analysis, through early season operations for delineation of your fields and variable rate seeding. But really, most of what people use it for today is during the growing season to look at the crops as they grow and to find areas of disease or infestation and find them before they get too bad. We can also use it for harvest management and planning. And we'll go through all of these in detail. During the planting portion of the year, over the winter time, you can use historical data to figure out the productivity of different portions of your field and areas where you've historically had pest and disease outbreaks. You can use that to do delineation of your field to figure out how to manage different portions of your field in different ways, or plant different things in different parts of your field. During early season operations, you can use it for soil preparation. One of the things that we can look at from space is soil organic matter content. So using an index called the brightness index and an index called the redness index, we can actually get the content of an organic matter in a bare field. Using this along with the delineation that you've done, you can create zones that are used for variable rate and selective seeding to figure out what to plant where and how much of it to plant. During the season is, again, where most people really use this information. Finding areas of problems in your field, finding disease outbreaks, finding pest outbreaks, and finding them before they get too bad. And some of the farmers that have been using precision ag platforms like this have stated up to 90% reduction in damage just by finding the issue earlier. It's especially true for really big fields. For smaller fields that you can actually physically walk around, you probably are seeing things happening as they happen. But for a really big field that you can't physically walk through and see with your own eyes, all of it, that's where this becomes really interesting. And part of this is through directed scouting. If you have information on what is healthy and what's not, instead of wandering around through the field, you can actually direct yourself to the hot spots where things are happening. So most of our partners have phone apps. So with your phone app, you can actually see the hot spots of vegetation health issues. And you can use the GPS on your smartphone to actually go to that spot in the field and find it. From there, a lot of the applications have the ability to take pictures of it to start to document the issue, and you can share that with your agronomist or with your team. We can also use this data to do variable rate treatments. And this is another big part of how it makes you more productive and saves you money. Once you know where in the field, in season, the issues are, you can actually direct your fertilizer and treatment to the areas that actually need it. So instead of dumping fertilizer at an equal rate across the entire field, you can actually do it variably and drop it only where it's actually needed, or drop more where it's needed and less where it's not. And the last area is in harvest management. From satellite imagery, we can actually see what areas of the field are drier than others, to plan and prioritize your harvest, to look at moisture content and actually plan harvesting some areas first and some areas later based on that. Now, a lot of people ask, why did we create satellites that do daily imaging? Why do you need daily imaging? What does that do for you? Well, first of all, we do daily imaging everywhere, the entire world. And so for any location anywhere in the world, we have at least 1,200 images of that piece of land. So of your farm field, we have 1,200 images, guaranteed, and growing. We actually download about 10 terabytes per day of data from space. It's a lot of pictures. And here's what daily looks like. On the left-hand side, you can see the daily images that go by. For some farmers and partners, they don't want to see every day. They actually want to see the best image every 5 days, and so we can process that and show them that instead. But you can see how the field changes over time. Now, in a place like Salinas or in the Central Valley where you don't have a lot of clouds, we'll probably have about 24 or 25 images per month of your field. The only days we won't have an image is if it's completely socked in with cloud cover or for random incidents where we don't have a satellite overhead that day. But for other areas of the world, they have a lot of clouds. Here is one area of the world where they have more clouds than just about anywhere else. It's Indonesia. In Indonesia, if you look at the scale on this, the blue-green color denotes 70 to 80% cloud cover on average per day. So it's cloudy there all the time. So if you look at these graphs in East Java, in Indonesia, or in Sumatra, you're lucky, even with daily imagery, to get a few images a month where you can actually see the ground. Now, Iowa and Nebraska, Central Illinois are probably somewhere in between here. I grew up in Illinois, and in the summertime, it's pretty rare that you have a cloudless sky. There are a lot of days out of the week where you're going to have a cloud over your field when the satellite comes over. And that's really why we do daily. So Landsat is a US government satellite run by the US Geological Service and USDA. And they come over once a month. And over Indonesia, you get one cloudy picture per month. So odds are you might not see the ground any time per year on that satellite. There's another similar satellite run by the European governments called Sentinel. It comes over a couple times a month, and it's pretty similar. You're going to see a couple cloudy pictures per month. On ours, a lot of the days are grayed out because they're just socked in with clouds. You can't see anything. But imaging every day, you can still see the ground a few times a month. And it's kind of interesting talking to folks in those regions, whether it's there or in South America. They're ecstatic that you can see the ground once a month because they've never seen that before. So now we're going to go in a little case study about irrigation. So part of this is resolution. So our satellites take an image where every pixel on the screen is 3 meters on the ground, 3 meters by 3 meters, so 9 foot by 9 foot just about. Landsat is the US government satellite. It takes images at 30 meters. So 30 meters is 2 basketball courts next to each other, is 1 pixel. So when you look at an irrigated field, it looks like you forgot to wear your glasses today. You can't see a whole lot. Here's ours of the same field on, I think it's the next day. You can start to see the detail. What you can do with that detail is actually detect issues. You can start to see things like a plugged nozzle or water pressure issues. Start and stop issues, where you'll see that line across the screen, across that irrigated field. You can also see small areas of crop damage that on the US government satellite wouldn't even show up because it just gets averaged into 1 pixel. So here's a use case around that. So one of our partners is a company called Origin Ag. And Origin, you probably haven't heard of it here in the US. They do most of their work in Europe and Africa. And they had a farmer who started using their application during the season in Zambia, in Africa. And this is a great example because they actually have an aerial photo of what happened. So while the customer was using the software, they actually saw an issue. And you can see that issue show up on the computer screen on the left. It's really clear that you can actually see the damage to those crops happening while it's happening. They actually took a plane up to go look at it as well to take this image. And you can actually see faintly the damage from the air. But from the ground, as you're walking through the field, it was really hard to see that damage before it got too bad. And for this field, that damage represented 15% of that guy's yield. That could have been gone due to this issue that he may not have caught if he hadn't had the ability to see it. So another big area that people are talking about in the technology industry is machine learning and artificial intelligence. And what this really comes down to is using the data that we have, because we have mountains of data, but it's really hard for human beings to actually comb through all that data and make sense of any of it. So we need machines to get smarter about finding things for us. So here's an example of that. We had an agricultural trading company who wanted to know how many silo bags were in the entire country of Argentina to get an idea of the stored capacity of all the grain stored in Argentina on any given day. Now, if you've never used a silo bag before, silo bags or ag bags are gigantic tubes of material where you can store grain for long periods of time. In Argentina, it's really common because they have crazy currency fluctuations. So they might have inflation of 15, 10% plus or minus a day or a week. So they want to time that along with the price, the US dollar price of their grain, and sell it at the right point in time. That's why they store so much of it. So if you look at a satellite image of Argentina, it is full of silo bags. They're everywhere. Every single farmer has one. You won't see this in Illinois. You see a few, but not this many. So what we had to do is we use machine learning. So what this is, if you've ever used Facebook, you've uploaded a picture of yourself and you wondered, how does it know that I'm in that picture? It tags you automatically and knows. That's machine learning. How it works is you've tagged yourself enough to give the computer enough examples of who you are that it can find you again. We're doing a similar thing here with silo bags, where we had some person who had the thankless job of drawing little boxes around silo bags on satellite images for about a week. Her name is Mariana. She works with me. And she had to tag about 1,000 silo bags in Argentina. But once we give the computer enough examples of what a silo bag looks like, it can find them over and over again. So here's a zoom up of that. So here we can see what, 1, 2, 3, 4, 5, 6 silo bags, and the next month there are 3 more. Now what the traders want is not a picture. They don't really care to see the picture. They actually don't even want them. What they want is this. So here's the important part. If you look at the blue line on the top graph, that's a US dollar, US dollars and the count of silo bags. So the blue line is the count of silo bags through the year. So you can see at harvest time, you can see that spike up. So as they're harvesting, they're putting more silo bags out in the field and they're capturing more grain. You can also see it fluctuate over time. The peaks from year to year are not the same, and the valleys are not the same. The orange line is the price of soybeans in US dollars. So you can see when the price of soybeans is low in the first hump in the graph, people stored a lot more soybeans, and they kept them for a lot longer. In the second bump in 2018, the price of soybeans went up a lot. And when the price of soybeans went up, the use of silo bags went down. People sold that grain to market as soon as they got it. They weren't hanging on to it that much. Now the traders can use this because it's all about supply and demand. If you go back to your economics class from high school or college, they now know the entire stored supply of soybeans in the entire nation of Argentina, because we counted 152,000 silo bags, and we can estimate from a silo bag how much fits in there. Another good example of this is a company in Brazil wanted to figure out the growth of pivot irrigation throughout the entire country, because they wanted to figure out how many new pivot farms are coming up, how much water are they using, and how is that going to impact the streams that they're pulling from. So we were able to train a machine learning model that was really similar to the silo bags one, that found every pivot field in all of Brazil and counted them every other week. So this is just the tip of the iceberg, though. There are a lot of applications for this type of technology, and you're going to be seeing more and more of that as the industry progresses in precision ag. So what's next? So we've got about 100 and something satellites of these types in orbit. Most of them are capturing red, green, blue, and near infrared. The last 30 that we've put up, and all of the ones we're going to be putting up this year, are capturing 8 bands. So the new bands are light blue, another green band, yellow, and red edge. The green bands are the most important for ag. There's an index called the photoreflectance index that uses these two green bands, basically on the yellow side of green and on the blue side of green, to look at plant health. And the researchers at Stanford, and this has been validated through a lot of academic studies, have shown that this index shows plant stress about a week earlier than NDVI does. So we should be able to see plant stress before it affects yield. We added the yellow band to look at crop senescence, and we added the red edge band because even NDVI, which is kind of the tried and true method of looking at plant stress and health, is better when you use red edge, which is kind of between red and near infrared, barely visible, compared to using red. We're also doing what we call data harmonization, where we're taking data from multiple satellites, from the US government satellite, Landsat, from the European satellite called Sentinel, and we're mashing that data together, because some days there is a cloud over your field. But when the US government satellite comes over on the same day, or the European satellite might be over on the same day, there may not be a cloud when it comes over. So we can slice out the clouds in our image and actually stitch in their image, which may not have a cloud in it, giving you more cloud-free access to data. This industry is really exciting. What we're doing, nobody thought was possible 10 years ago. And what a lot of other companies in the new space industry are doing, nobody thought was possible 10 years ago. If you've seen the rocket launches that Elon Musk has done with SpaceX, they're pretty spectacular. No one thought that you can launch a rocket that has 3 big rocket cores and actually land all of them right next to each other at the same time. People thought that idea was nuts. No one actually thought that you can make things as small as we have. This satellite 20 years ago would have been the size of a full-size kitchen refrigerator. But now, using cell phone parts and parts going into digital cameras, we can make this a miniature thing and probably make it even smaller in the future. There are other companies that are doing miniaturization and also machine learning. So now that we have all of this data from us, from ground sensors, from weather satellites, from radar satellites, they're taking that and using machine learning, as I've shown you, to start to make sense of that data automatically, instead of having to have people look at it. And that's really where things are going. And all of this, a lot of it is being driven by academic studies. So there are hundreds of papers on ag remote sensing, as we call it, being published every year, advancing what we're doing and how it's coming to you. Any questions? A lot of them have been driven by military intelligence. So, for example, the US government would like to know where every Russian bomber is every day. Another one is ship detection. So the US government would also like to know if ships, if fishing vessels are in areas that they're not supposed to be, in protected marine areas. Or if a large warship is driving someplace that we didn't know it was. So that's driving a lot of it, but the use cases outside of that are just getting started. We had one that was really interesting. A guy wanted to know, find me every football field in the state of Georgia, because he sells artificial turf. So he wanted to know every football field in the entire state of Georgia and whether or not they had artificial turf. And we were able to actually define that. We had another guy, this is in Japan, they wanted to see every power plant, every coal-fired power plant in the entire continent of Asia. And interestingly, they wanted to do that because they sell parts for coal-fired power plants. And they wanted to see if the smokestacks were generating steam or not. Because if a coal power plant is shut down, that means they probably have maintenance issues, and they might need parts. Another really interesting one is from the energy industry. We have a company that looks at every oil field in the world and counts the number of new wells every week. They also look at every oil storage tank in the entire world, because the tops of those things float. So by looking at the shadow generated by the sun hitting the edge of the barrel, you can actually detect how much oil is in there. And they calculate every week how much oil is in every oil storage tank in the world. Forestry is another big industry for us. So they want to look at, like agriculture, they want to look at pest and disease outbreak, but they also want to look at the amount of timber harvested. A lot of times, timberland is owned by people who are kind of landlords, but they're not actually harvesting the timber. They have other people come in and do it. And they want to actually see if I've given you a contract to harvest 10 acres of forest, did you really harvest 10 acres? And for contract workers, they actually pay them based on our data. So if you said that you're going to cut down 10 acres today, we're going to check and make sure you did. And if you didn't, we're actually going to pay you what you actually cut down. Yeah, so are we doing just basic modeling or search and find? A lot of it right now is search and find. It's search and find combined with other data sets sometimes. So we have seen some people who are really on the cutting edge of the ag world especially, who are doing things like find the spot in the field that is not looking good, but then also layering on top of that weather data and agronomic data to say, if you're growing sugarcane in Southeast Asia and you had a wet year and the temperatures have been around this, then what you're seeing in that spot that's not doing well is probably this. So it's semi-predictive. We're also seeing drone integration just starting. So for example, we can show a spot on the field that's not doing well, but we don't know why it's not doing well. We just see that something does not look healthy. But what if you could have a drone automatically fly to the spots that are not doing well instead of walking there, and fly low enough to see the leaves and see the fruit and see what's happening? And we're seeing that starting as well. Great question. So thermal imaging, especially there's a band further down the spectrum from near infrared called SWIR, shortwave infrared, that can do water and moisture content detection. It can also do things like methane detection. Right now, those sensors are about the size of this podium just for the sensor, and they take about 2,000 watts. So we can't yet quite put them in a small satellite, but we're actually trying to develop sensors with NASA JPL that can be small enough to put those sensors on board. Only on the surface. So yeah, we can only see the surface of it. And so it's measuring it by two indicators called soil brightness and soil redness. And those are pretty well academically correlated. But one thing that came to mind yesterday that I really have to check on is, if you're doing no-till, how does that work? Because you have a lot of residue on the field. And I don't know if they've done correlative studies on no-till for that index. I think it's all been on tilled farm. Yeah, as the resolution increases, the privacy concerns become larger. Right now, we can't see people. We can see vehicles as kind of like one dot, two dots sometimes. But as the resolution increases, you could actually see more, and it will become more of a concern. Right now, everybody kind of knows that this is happening, and there's not much you can do about it. So international treaties have basically said that satellites can fly over everywhere in the world, take pictures of anywhere, and no one can stop it. Well, thank you everyone for coming. I really do appreciate it. If you have questions that come up later, please reach out to me. I'll give my contact information out to anybody who wants it. And like I said, if you're in San Francisco and want to come visit, let me know.